Friction. What exactly is friction? Friction is the opposing force which comes into play when a solid body moves or tends to move over the surface of the other body when they are in contact. So say for example we have a body over a surface. These two bodies will tend to experience a force of friction, due to which when we pull this body in this direction, this body will oppose the motion of the body on top, due to which the motion of this body will be restricted. So say we have, this is our body A, this is body B. We are trying to pull body A, but due to friction, which is the opposition to the motion of A will not be able to move easily due to this frictional force. So how does frictional force come into existence? Frictional force arises between two surfaces because of one, strong atomic forces or molecular forces of attraction between two surfaces, or interlocking between two surfaces. This interlocking may also be due to irregularities in the surface. So due to irregularities in the surface, frictional force will occur, due to which the movement of body A over body B will be obstructed. So friction can have a lot of advantages as well as disadvantages. So we can walk or drive a vehicle on the road because of friction. So the motion of a vehicle on the road is smooth due to friction, and therefore we do not waste a lot of fuel while we are driving. Otherwise, the car would not slip on the road due to friction. While due to friction, as we have too many irregularities in the road, more fuel would be needed, and therefore this would also be a disadvantage in certain cases. So how does this frictional force come into play? This happens because when there is a relative motion or even a tendency between two interacting bodies pressed directly against each other to move, this frictional force comes into play. So say for example, we have the same example of a body A which is placed on body B. This is the equilibrium state where body A is just placed on body B. Due to this, there would be a force which would be acting normal to the surface given by the normal reaction, and this force acts perpendicular to the surface B, and there is a force of static friction given by F, which is the force which is a self-adjusting force, and it is a limiting force, which means that this force resists the attempt to move body A over body B. So static friction is the force which resists the motion of the body over a surface. This force of static friction is a self-adjusting force. So what do we mean by self-adjusting? A self-adjusting force is nothing but a force which comes into existence when we change the direction of limiting force, Say for example, we have the limiting force in this direction. If we suddenly change the force in this direction, the magnitude of the force decreases, and therefore the magnetic magnitude of the static friction, the force of static friction decreases, and therefore we call it self-adjusting. So as we've seen, static friction is the force which resists the motion of the body or surface. So basically, when we're trying to move body A over body B, the first force which acts on body A is the static friction, which opposes the movement of body A. So body A will try to overcome this force of static friction, and once it has overcome the limiting force of static friction, body A will move over body B. And as body A is moving over body B, the motion of body A will still be restricted by a force known as the force of kinetic friction. This force of kinetic friction between two bodies in contact occurs when one body is sliding over the other. It is also known as dynamic friction as the body is moving. So we have covered two basic types of forces. This force is a force which is always opposing the motion and will act in the opposite direction. This acts normally. So this is perpendicular to the surface, while this acts in a direction opposite to the direction of motion. While a third force which occurs is the rolling force. Now say for example we have a ramp, and on that ramp we place a ball. This ball will tend to roll over this ramp, and there will be a force opposing this motion. This force is known as the rolling force. So it is the force that comes into play when two bodies are in contact and one body is rolling over the other body. So how do these forces actually affect us in daily life? Now, for example, it is difficult to walk on sand because of force. We slip on a rainy day because of these forces. So these are all examples of how these forces actually affect us in daily life. So now we come to the topic coefficient of static friction. This coefficient of static friction comes into play when we study the laws of static friction. The first law of static friction states that the limiting force of static friction is directly proportional to the normal reaction between the two surfaces in contact. So say for example, we have this body placed on the surface, we have the normal reaction N, and we have Fs. So we have Fs which is directly proportional to N, and we remove this constant of proportionality which makes Fs equal to mu s times N, where mu s is called the coefficient of static friction. So we can also say mu s is equal to Fs divided by N. So the limiting force of static friction is directly proportional to the normal reaction between the two surfaces. The coefficient of static friction is therefore defined as the static friction to the normal reaction. The second law of static friction states that the limiting force of static friction for any two given surfaces is independent of the apparent area as long as the bodies remain in contact with the same area. So say for example, we take the same example, body A on body B. As long as the area covered by body A, which is in contact with body B, is the same, there would be the force acting would be the same. The limiting force of static friction would also be the same. But as we change the body and as the area covered by the body is different, the force acting would be different, the force opposing would be different, and therefore the coefficient of static friction would also be different. As I stated, the second law of static friction states that the limiting force of static friction is independent of the apparent area of the body in contact. Let's take an example. We have a body A placed over body B. I have a pulley and I'm going to pull this with weights. Let's attach another body C to body A. So as I pull this, as I increase the weights, I'm going to place weights here. As I increase the weights, body A and body C will experience a limiting force of static friction. And as this limiting force of static friction is overcome, these two bodies will tend to move. Let's take a case 2. In this case, I'm going to place body A and body C one over the other. This is my surface B, and I'm going to attach the pulley with the weights. And here I apply my force with the weights. So what exactly is happening here? The normal force will tend to oppose the motion of body A and body C, that is the weights of body A and body C. And once we overcome the limiting force of static friction, body A and body C will tend to move. However, if we consider the limiting force of static friction Fs in case 1 and in case 2, we will notice that limiting force of static friction in case 2 is lesser than that in case 1, which means case 1 would have a higher force of static friction which has to be overcome, as the apparent area, which is the area of contact between the surfaces, is more in case of case 1 rather than case 2. So this is exactly what the second law of static friction tends to tell us. The third law of static friction states that the limiting force of static friction depends on the nature and material of the surfaces in contact. Now say for example, I'm using a wooden surface. A wooden surface which has a lot of irregularities. So I have this kind of a surface and I tend to move my body A over this kind of a surface. And then once I note the coefficient of static friction, I take another surface which is also wooden surface, but the same surface I'm going to polish the surface. So I have a polished surface. After polishing the surface, I tend to find that Fs2 will be lesser than Fs1. So the coefficient of static friction is dependent on the nature of the material of the surfaces which are in contact with each other. The second law of static friction states that the limiting force of static friction is independent of the apparent area in contact. Now let's take for example, I have my surface B, I have a body A which is attached to a body C, and I have a pulley which is attached, to which I have weights. So these weights are going to be pulling these bodies down. Now, as this force increases at a certain point, at a certain limiting force of static friction, after it overcomes that limiting force of static friction, body A and body C will tend to move in this direction as we keep on increasing the weights. Now, This is case 1. In case 2, we have the same surface, but in this case, we are going to be placing body A and body C over each other. And we connect this here, the pulley, and then we have weights. So as we increase the weights, these two bodies will also tend to move after the limiting force of static friction is overcome. So let this have a limiting force of static friction Fs1 and this have a limiting force of static friction Fs2. We see that Fs1 is equal to Fs2. So the limiting force of static friction does not depend on the area of the bodies in contact. It is independent of the areas of the bodies in contact. The third law states that the limiting force of static friction is independent of the nature and the material of the two bodies in contact. This means that, say for example, it's dependent on the areas and the materials of the bodies in contact. Say for example, we have a wooden surface with irregularities like this, and I place my body A over this, and I tend to move it. And then I calculate my limiting force of static friction, Fs1. And then I am going to smoothen this surface by polishing it, and I obtain a flat surface. And then I tend to find my limiting force of static friction, Fs2. In this case, I observe that Fs1 will be greater than Fs2. This is because the limiting force of static friction depends on the material, the nature and the material. So if there are more irregularities, if there are more discontinuities, if the two bodies uh, are going to be full of friction, it's going to oppose the motion and therefore the motion will reduce. So similar to the forces of static friction, we have the forces of dynamic friction. And the laws of dynamic friction or kinetic friction are similar to the laws of static friction. So the first law of dynamic friction also states that the force of dynamic friction or kinetic friction is directly proportional to the normal reaction between the two surfaces in contact, which means that Fk in this, let's say Fk is directly proportional to N, and therefore Fk is equal to mu k times N, where mu k is called the coefficient of kinetic friction. So we have mu k equal to Fk divided by N. So the coefficient of static friction is the force of kinetic friction divided by the normal reaction. So it's a ratio of the force of kinetic friction and the normal reaction between the two surfaces. The second law of kinetic friction also states that the force of kinetic friction does not depend upon the shape and the apparent area of the surfaces in contact. That is similar to the force of static friction. So the same second law, all the concepts of second law are applicable to kinetic friction as well. While the third law states that the force of kinetic friction depends upon the nature and the material of the surfaces in contact, which is also same in case of static friction. So we see that the second law and third law of static friction and dynamic friction are almost the same, except for the fact that this occurs when the two bodies are in equilibrium, while this occurs when the two bodies are moving against each other. So similar to the laws of static and kinetic friction, we also have the laws of rolling friction. So the basic law of rolling friction states that the limiting force of rolling friction Fr is directly proportional to the normal reaction. So Fr is equal to mu r times n, where mu r is known as the coefficient of rolling friction. And mu r is equal to Fr upon n. So the coefficient of rolling friction is the ratio of the limiting force of rolling friction to the normal reaction force. After seeing the various laws of static, dynamic, and rolling friction, let's move to what is known as the angle of friction. So as we stated that if we have a surface and we have a body placed on that surface, so this is body A on body B, this is my normal reaction force given by N, and this is my force of static friction F. Then we have the resultant, which is given by a vector A, where vector A makes an angle of theta with the normal. So this turns out to be, so let's say that this is our origin this is B, this is A, and this is N. So in this triangle, AB upon OB is equal to cot of theta, as theta is the angle between the resultant and the normal. So OB is equal to AB upon cot theta. Therefore, OB is equal to AB tan theta, or tan theta is equal to OB upon AB. But OB was actually the limiting force of static friction, while AB is the resultant. It's the normal force N. And therefore we get, but F by N is basically my equation for mu. So I say mu is equal to tan of theta. So my angle of friction is basically the inverse tan. So angle of friction theta is the inverse tan of my coefficient of static friction. Definition, the angle of friction is basically the angle made by the resultant force A with the vertical force or the normal reaction force N. The next concept that we'll be moving on to is the angle of repose. So we have the angle of repose. So the angle of repose is let's take for example, the angle of repose is basically the angle which an inclined plane makes with the horizontal so that a body placed over it just begins to slide off its own accord. So we have an inclined plane and we have a body placed over it. The weight of the body is mg, which acts vertically downwards. And we have the normal reaction force N, which is acting perpendicular to the surface. F is the limiting force of static friction. So let this be our coordinate axis. So this is my y-axis and this would mean my x-axis. This angle theta is known as the angle of repose. So you want to know what exactly this angle of repose, what is the numerical value of this angle of repose. So to find that out, let us resolve these vectors in the x and y direction. So according to the x direction, so in the x-axis, along the x-axis we have mg sine theta. So that's this sine theta minus F, which is the opposing force, this would be equal to 0. So we have mg sine theta and this is F, both equal and opposite. So mg sine theta minus F is equal to 0. Along the y-axis, we have n, which is equal to mg cos theta, which is basically the weight along the x-axis, sorry, the y-axis, and this is the relation. So basically we have n minus mg cos theta, which is equal to 0. So n is equal to mg cos theta while f is equal to mg sin theta. But we know that f is directly proportional to n. So f is equal to mu times n, which means that mg sin theta is equal to mu times, say like for example in static friction, mu s times, so mu s times n, that's mu s times mg cos theta. So once we get rid of the common terms, we get mu s is equal to sine theta upon cos theta, which is equal to tan theta. So this basically means that my coefficient of static friction, so here we say that for the body to move, F has to be greater than equal to, has to be lesser than equal to the limiting force of static friction, Fs, is lesser than equal to mu s times n. So let's apply that here as well. So let's say less than equal to, so mu s has to be greater than equal to tan theta. So mu s will be greater than equal to tan theta. This is my relation for my angle of repose. So my angle of repose theta is equal to tan inverse times mu s. So this is my angle of repose. So this means that the coefficient of static friction between the two surfaces, in order that the body does not slide down, should be greater than, should be lesser than tan inverse of mu s. So as we increase tan theta beyond mu, the body begins to slide. This is known as the angle of repose.